Hey there, my name is Alejandro, and welcome back for day 7 of me doing the NeetCode 150 challenge. So today's problem is for October 14th, 2024, and let's get straight into it. Okay, today we get a LeetCode Easy problem 704, binary search. Okay, given an array of integer nums, which is sorted in ascending order, and an integer target, write a function to search target in nums. If target exists, then return its index, otherwise return -1. You must write an algorithm with O of log n runtime complexity. Okay, this is probably one of the most infamous computer science algorithms of all time. So essentially, yep, you have an array of numbers that is listed in sorted order, and you want to find if a certain number target exists, right? And so what do you have to return here? Its index. So we don't return true or false, we just straight up return its index. Makes sense. So the easy way would be literally just to be like, okay, for I in range length, whoops, okay, lagging a little bit, range of length of nums, if nums of I is equal to target, then return I, right? Otherwise return -1 if it doesn't exist. Okay, cool. Otherwise, so we return -1. So this will work, right? So this gets accepted, and I wonder if we time limit exceed here, right? Oh, we actually don't. Okay, and the fact we beat 44% is actually very concerning, right? So it's okay, like a lot of solutions in here, but we can do much better. In fact, one of the constraints for this problem is that you must run an algorithm with O of log n time complexity, right? And so the idea is very straightforward, right? You kind of leverage the fact that this array is sorted, right? So, sorry. What you can do is essentially look at the middle element of the array. And then from that point, you can make a decision, right? Let's say the middle element here is 5, right? And we are looking for a target of 9. Well, since we know that the array is sorted and our current, element that we're looking at in the middle is 5, then we know that 9 is going to belong in the right subhalf of the array, right? Because since this array is sorted, numbers that are less than 5 or equal to it will be on the left half of the subarray, and numbers that are equal to 5 or greater will be on the right side of the subarray, right? And so since 9 is greater than 5, then we know that it will be on the right side of this 5, right? So essentially, the point is that we can keep doing this recursively over and over again, and every single time we look at an integer, we make a decision of, okay, will we look at the right side or the left side, right? And if you split it down in the middle evenly, then essentially every single iteration, you're going to be able to cut down half of the elements, right? So essentially you go from n to n over 2 to n over 2 over 2, which is n over 4, to this divided by 2, n over 8, and so on. And so essentially, how many times can you divide n by 2 until you get to 1? Well, log n, right? Because again, like the number of times that you can divide n by 2, well, that's like by definition of logarithmic, right? So essentially it's like there will be a total of log n steps here, right? So you keep cutting the array size in half. So let's just go ahead and do that. We can do a recursive and an iterative solution. So let's do iterative solution, right? So if you can never choose between a recursive and an iterative solution, 99% of times you should always pick the iterative solution, unless there's like, you know, a huge amount of overhead otherwise and so on, because any recursively written solution can also be written iteratively, but sometimes it could be a big pain in the butt. But here for something like binary search, if anything, it actually makes things easier. So let's set up our left and right pointers here to 0 and comma length of nums -1. And here, essentially, we're going to say, okay, while L is less than R, we're essentially going to say, okay, mid is equal to L plus R over 2, right? So this is our middle index. If nums of mid is equal to target, then we can return, our current index, right? So return mid, right? So this index contains our target, so we just return it, right? Otherwise, here we will return -1 if we find nothing, right? Otherwise, we'll say elif nums of, if target is smaller than our current nums of mid, right? That means it belongs in the left subhalf. So what we can do is we set a right pointer to be equal to mid -1, right? Because anything that is mid and greater in indices of values will each have values that are greater than target, so they can be safely ignored, right? Or otherwise, here we'll just do assert that, you know, target is greater than nums of mid, right? But the point is that, like, okay, target is greater than the number at index mid. Since we know it's a sorted array, any number that is before this index as well will be smaller than target as well, right? So essentially, if target exists, it must be in the right subarray, right? In which case, we just say, okay, skip over every element from 0 to mid. So we'll set our left pointer to be equal to mid plus 1, right? And otherwise, we return -1 at the very end. So I think that something like this will work. There we go. Let's press submit, and now we should get a much, much faster runtime complexity. Okay, so we had a little bug here. Oh, maybe it's something like that, right? There we go. Okay, that's my bad. Yeah, so if L is equal to R, you also want to check if that exact indice is the event. Okay, so we get 38% and so on. Maybe it's like they don't have, like, you know, strong enough test cases that where we can, like, really leverage the logarithmic part. Which actually surprises me. Somehow the logarithmic solution was slower than the linear one. That's actually kind of crazy. Okay. Well, but in actual asymptotic complexities, this log n algorithm is way faster than whatchamacallit, the linear times solution one, right? Especially as n grows large, this is just infinitely faster than the linear solution, or I should say exponentially faster. But yeah, that's just me being that guy, let's say. But yeah, otherwise, again, in all my videos, I do a quick recap of how I was able to solve this problem. Essentially, again, all you do here is you leverage the fact that the array is sorted. So you look at the middle of the array, and essentially from there you make a decision, right? Our target is 9. So since we know that the array is sorted from 5, we know, okay, any element that is before this index we know will be of value smaller than or equal to 5. So 9 will definitely not be in there. So instead, we can search in the right half of the subarray to see if 9 exists, right? And so we keep doing this and quote unquote splitting the array in half each time. So there will be a total of log n steps. And at the very end, if we still have not found our target, then that means it does not exist in the array. And that's why we return -1. So again, just very, very extremely classical computer science algorithm. You will learn this algorithm in almost any computer science class where you do searching, sorting, and so on. Any of those common basic algorithms. In fact, if you're brand new to computer science and so on, and you want a good place to start, I'd highly recommend something like the Harvard CS50 lectures online and so on. And those lectures, I have actually watched them myself just for fun. And yeah, of course, like one of the algorithms they cover is binary search. I think it's actually lecture 1, where like David J. Milan has like that he grabs like a dictionary and he's like, okay, what's one way of searching the dictionary? Oh, you could go like, you know, word by word until you reach the word that you want. But obviously no one does that and so on. And so we implicitly as humans use binary search. You go to the middle of the dictionary, right? And you see like, you know, the M's, but your word is zebra, right? So it's like, okay, you scratch the left half because you know that the word zebra is going to come in the right half of the dictionary. So then you like, you know, you look again like through the half and keep doing, you know, your little binary search and so on. So I think it might not be the very first lecture, it might be like the second lecture or something, but like one of the very early lectures, that's like one of his main lessons and so on. So yeah, so super core algorithm if you do not know it already, and if you want a good place to start and you don't know this algorithm, I'd highly recommend something like CS50. They're worth a watch, definitely big time. But otherwise, that's pretty much it for this video, and as always, that means we can now check another problem of the NeetCode 150. If you did like or find this video useful, I would highly appreciate if you left a like or a comment, and otherwise, I will catch you in the next one. So until then, ciao, my friend. Bye-bye.